Oxidation-reduction reactions. We've been talking about different types of reactions. In this group of reactions, we have electrons being transferred. So electrons are transferred from one of the reactants to another. So oxidation reduction, lots of syllables. It's often called a redox reaction. Reduction, oxidation. Always reminds me of Redbox and makes me want popcorn, but it's redox without the B. So many, but not all, redox reactions involve something reacting with oxygen. And that's actually where the term oxidation came from. It was something reacting with oxygen. So they said it was oxidized. So here's examples of iron reacting with oxygen, forming rust. That's an oxidation reaction. Octane burning, we looked at that one earlier. That's oxidation reduction. And hydrogen reacting with oxygen to form water is also an oxidation reduction reaction. So those are examples of things reacting with oxygen. So what's happening here, hydrogen gas and oxygen gas react to form water in the gas state. It's in the gas state here because this happens with the release of a lot of energy. It's actually quite explosive. So here we have an innocent-looking balloon, but it's filled with hydrogen and oxygen gases. And so you give that a little spark, and you get kaboom, and that's going to be enough of a kaboom that's going to lift the ceiling tiles. It's a big reaction. So that's a combustion reaction. Combustion is something burning. And what's necessary for something to burn? Oxygen. Oxygen present in the air is needed for burning. So something reacting with oxygen, generally called combustion, it is a redox reaction. We can also have redox without combustion. No oxygen involved. So here we have the element sodium reacting with chlorine. This is a photograph of this occurring. So chlorine is this yellowish gas, and sodium is a metal. And those will react to form table salt, sodium chloride. What happens here is that there are electrons being transferred from the sodium atoms to the chlorine. And so we end up with sodium ions and chloride ions. And so we see there's an electron transfer there. So that is an example of a reaction of a metal with a nonmetal. Sodium is a metal, chlorine is a nonmetal. Those sorts of reactions are redox reactions. Sodium reacting with oxygen. That could be called a combustion reaction. But again, it's a metal-nonmetal reaction, sodium and chlorine. So these are metals and nonmetals, but we also have the conversion of free elements into ions. So the sodium atoms lose an electron. They give the electron to oxygen. The oxygen gains an electron. So then we have sodium cations, oxygen anions. And the same thing will happen with sodium and chlorine. The sodium will transfer an electron to the chlorine, forming positive and negative ions. It's a transfer of electrons. Any questions? If one element loses electrons, another element has to gain electrons. And conversely, if there's an atom that is gaining electrons, something else must be losing them. There's no electron bank or electron homeless shelter where you can go and get stray electrons. Electrons are attached to atoms or ions. And so you can only get them from other atoms or ions. So the atom that loses the electron, we say, is being oxidized, and the atom that gains the electron is being reduced. So here we see that sodium is losing an electron. It's going from a neutral sodium atom to a positive ion by losing an electron. The sodium atom is oxidized. The chlorine is gaining electrons to form chloride ions, and that's called a reduction. So we have oxidation and reduction occurring at the same time. So we have to remember which is which. One's gaining electrons, one's losing electrons. One way to remember this is oil rig. OIL-RIG. Oxidation is loss of electrons. Reduction is gain of electrons. This is one of those things that I still, when I need to identify oxidation reduction, I still run oil rig through my head because I don't do this all the time, just in certain chapters, and so I get a little rusty on it. So oil rig, oxidation is loss, reduction is gain of electrons. Any questions? So we were looking there at a complete transfer of electrons. We had atoms and we're forming ions. But we can also have a partial transfer of electrons, a transfer of electron density. So if we have two nonmetals, such as hydrogen and chlorine, reacting to form hydrogen chloride gas, we're not naming this as an acid here because it's not dissolved in water. Let's look at the picture over here. So we have a hydrogen diatomic molecule and a chlorine diatomic molecule. These two hydrogens are sharing electrons. That's what's holding them together in the bond, and so we see there's this increased electron density between the two atoms. Same thing occurs with the chlorine. Two identical atoms are going to share equally. When these react and form hydrogen chloride molecules, the chlorine has a stronger attraction for the electrons. It tends to hog the blankets. If these two are sharing a bed, the chlorine is hogging the blankets, and hydrogen's kind of left out in the cold. So hydrogen, this end of the molecule, is going to have a slight positive charge, and the chlorine end is going to have a slight negative charge. Not enough that it's actually ions, but it's a charge imbalance. And so electron density has been moved from the hydrogen to the chlorine. So it's a partial electron transfer. Any questions? So here we can think of reduction is gain of electron density. So the chlorine has gained electron density. It has been reduced. The hydrogen has lost electron density. It has been oxidized. So when we have nonmetals reacting like that, it's much harder to identify which one has gained and which one has lost electron density. And so what we do to keep track of that is we use something called an oxidation state or an oxidation number. Now this is something that we just made up to help us keep track of what's being oxidized and what's being reduced. It's just a method of tracking electrons. It's very important to remember that oxidation states are not ion charges. And what's confusing about that is often the oxidation state is the same as the charge on an ion, but you can have an oxidation state that's not zero and not have a charge. So they often overlap with each other, but oxidation states are not ion charges. They are imaginary charges assigned by a set of rules, whereas ion charges are real and measurable. Oxidation states are not, they're imaginary. So we need to learn how to assign oxidation states. I'll go through the rules. They seem kind of confusing, but then hopefully I can summarize at the end and show you that it's really not all that bad. So the rules, and they go in order of priority. So you do the first rule and then the second rule, etc. So free elements have an oxidation state of 0. So if you have like pure sodium metal, you have chlorine diatomic molecules, just one element, the oxidation state is 0. And that corresponds to the ionic charge that those things have, which is 0. They don't have an ionic charge, right? If you have monatomic ions like sodium ion and chloride ion in sodium chloride, their oxidation state is equal to their charge. Okay, so if you have barium 2+ ion, what's its oxidation state? 2+. And O2- has an oxidation state of 2-. So if you have a simple ion, not like phosphate or something, but chloride, sulfide, nitride, those sorts of things, the oxidation state is the same number as the ionic charge. That's why we sometimes get them a little confused. Like ionic charges, all of the oxidation states have to add up to particular things. So if we have a neutral molecule, here we have a neutral charge, well, a neutral formula unit. We know that the charges have to add up to 0. The charges are the same for ions as their ion charges, and so the oxidation states add up to 0 as well. Okay, so if we have a neutral compound, all of the oxidation states have to add up to 0. If we have a polyatomic ion, such as nitrate ion, so nitrate ion has an overall charge of -1. And it's got these nonmetals in it. There's 1 nitrogen atom and there's 3 oxygen atoms. And all together, there's a -1 charge. The oxidation states of the elements in this compound, their oxidation states have to add up to equal the charge on the polyatomic ion. Metals always have positive oxidation states. Their oxidation states are the same as their charges. It's the nonmetals that take a little more remembering. And so we have this table, and you go down in order. Fluorine, hydrogen, oxygen, then group 7A elements, group 6A, group 5A. These are for the nonmetals. Because if you think about it, if you have a compound between nitrogen and oxygen, you have N2O or NO2, there's all kinds of different ones. How do you decide which one's the positive and which one's the negative, right? It's actually based on electronegativities, but that gets a little bit muddy, and so we've set up these rules. You remember the rules, and then there's a lot less thinking involved. So this is like a list of these nonmetals saying, well, I want this charge, I want this oxidation state. No, I want this oxidation state. How do you decide what they get? You go down the list. Fluorine always gets first priority. Fluorine wants to be -1 for its oxidation state. When fluorine becomes an ion, what is its charge? -1, right? Next up is hydrogen. When hydrogen becomes an ion, what is its charge? +1, right? Next down the list is oxygen. What charge does an oxygen ion have? -2. These oxidation states are the same number as an ion charge if these were ions. Okay? So it's not really that we need to remember a bunch of new numbers. They want to have an oxidation state equal to their ion charge, except here they're not actually ions. Does that make sense? So after those 3, then we go anybody in group 7, anybody in group 6A, anybody in group 5A, and they're going to get the oxidation state that would equal the charge if they were an ion. So remembering the oxidation states isn't too bad because it's the same as the ion charges, but the list is a little tricky. So this is what I came up with. Do you know what pho is? Really good noodle soup, right? Yummy, yummy stuff. So pho. Well, what if, let me make sure I do this right. What if we just cut a little bit of the P off? You could still pronounce that pho, right? Fluorine, hydrogen, oxygen. 7, 6, 5. I think there's actually a restaurant that's pho 76. I should open one, pho 765. Spell pho wrong and talk about oxidation states. This is how I remember it, pho 765. So We're looking at the elements here, trying to decide who gets what they want. Fluorine, hydrogen, oxygen, somebody in group 7, somebody in group 6, somebody in group 5. So we'll do some examples. A couple other things. You can have fractional oxidation states. You can't have a fractional charge on an ion, right? You can't have an O minus 1/2 ion, because how can you lose half of an electron? Fractional oxidation states are possible because this is not necessarily a full transfer of an electron. It can be a shift of electron density. I don't think we're going to run into any, but just be aware that those can happen. I'm not going to trick you on this, but when we use oxidation states, we write the sign before the number, like here. And when we write ion charges, we write the sign after the number, right? So if we say that oxygen as an ion has a 2- charge, it has a -2 oxidation state. Just very subtle difference. I'm not going to hold you to that, but I'm going to follow it. Okay, let's do some examples. We need to be able to assign oxidation states. So here we've got chromium. So is that an element all by itself? Yeah. What's its oxidation state? 0. So the oxidation state here is 0. Now as we do these, if you're like, how the heck did you do that? Please ask, okay? This is a chromium atom. It has no charge on it. The oxidation state's the same as its charge, which is 0. How about a chromium 3 ion? -3 is too hard. +3. It's the same as the charge, okay? So the charge is 3+. The oxidation state is +3. It's just the same. Okay, here we've got carbon tetrachloride. This is a carbon and 4 chlorines. So we've got a carbon, we've got chlorine, 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 chlorine. So we have 2 nonmetals. We have to decide who gets first choice. Well, Fe765. Fluorine, nope. Hydrogen, nope. Oxygen, nope. Group 7, yep. Chlorine is in group 7, and so it gets to choose its oxidation state before carbon. What would chlorine like to be? -1, right? Because that is the same as the charge it takes. So each of those chlorine atoms gets an oxidation state of -1. So from the chlorines, we have a total of -4 in the oxidation states. That is not a charge, it's an oxidation state, sort of a pretend charge. And then there's 1 carbon over here. This is a neutral molecule, so the oxidation states all have to add up to 0. So what does carbon have to be? +4. So the carbon has to be +4. We are assigning these oxidation states in the same way that we assigned charges when we were looking at the transition metals. Like if this was molybdenum or vanadium or something and we're trying to figure out what the charge on the ion would be, it's the same process. Okay? So the carbon has a +4 oxidation state, and each of the chlorines has a -1 oxidation state. Each atom has its own oxidation state. You've got 4 chlorines. You can't say, well, you're going to be 0 and you're going to be 5. They're all going to be the same. It's like small children. No, you have to treat us all exactly the same. If he got 1.5 cookies, I get 1.5 cookies, right? You can't just give me 1 cookie. So any questions about that one? Yeah.
So we just have to memorize these rules, right?
You need to memorize the rules, which, Fe765, that's not so bad, right? Noodles.
I meant so we have to know that that's a neutral molecule and go through the other table list of -765.
Right. So the thing is, it's very similar to ion charges, okay? So most of this is the same thing we would do with ion charges. The difference is the Fe765 thing, but there we're just deciding who gets the oxidation state that matches the charge they would have as an ion. okay? And so you got a neutral molecule, oxidation states have to add up to 0. Just like here, we have an ionic compound, and all the charges add up to 0, right? So the oxidation states add up to 0 as well. Let's look at this one. So we've got strontium and bromine. Well, strontium is a metal, and bromine is a nonmetal. This is an ionic compound, isn't it? There's 2 bromines. What are the charges on these ions? Well, strontium's +2, and bromine is -1, right? Just from their position on the periodic table. This is a strontium ion. Its oxidation state is the same as its charge. So for the strontium, the oxidation state is +2. Each bromine has an oxidation state of -1. Yeah?
Now, when you are writing, when they ask for what the oxidation state is, and if it's a compound like that, you want it for each element.
Yes.
There's not one single.
Correct. So when you have a compound, a polyatomic ion, anytime you have more than a single atom, each atom has its own oxidation state. If you have multiple of the same element, their oxidation states will be the same as each other, but they each have an oxidation state. Very good question. What about SO3? So we've got a sulfur, and we've got 3 oxygens. 2 nonmetals. This is not an ionic compound. We can't look at ions. So that's when we do the 765 thing. They are both in the same group. They're both in group 6, right? But FHO. Oh, yeah, exactly. Oh. So fluorine? Nope. Hydrogen? Nope. Oxygen? Yes. There's oxygen. Oxygen is in the same group as sulfur, but oxygen gets to choose first. So the oxygen has, well, I shouldn't write them as charges. Each oxygen has a -2 formal charge. Oxidation state. The sulfur would also like to have a -2 oxidation state, but it doesn't get what it wants here. Oxygen got first choice. Sulfur needs to take whatever is left. This is a neutral molecule. The oxidation states have to add up to 0. So it's +6. So the sulfur has a +6 oxidation state. Is it super happy about that? Probably not. Tough, those are the rules. That's what happens. So in SO3, the sulfur is +6, and each of the oxygens is -2. Let's do nitrate. So here we have 1 nitrogen, 3 oxygens, again, nonmetals, Fe765, fluorine, no, hydrogen, no, oxygen. So the oxygen wants to be -2, and so it gets what it wants. And the nitrogen has to make up the difference. But what do these oxidation states have to add up to for this ion? They have to add up to the same charge as is on the ion. So the oxidation states have to add up to -1. So this is -6 from all 3 oxygens, and we want something here that when we add it to -6, we get -1. It's +5. So the nitrogen must be +5. 1 +5 and 3 -2s add up to the overall charge on this ion. Any questions? It's going to take a little practice, huh? We need to be able to recognize redox reactions and to identify what thing is being oxidized, what thing is being reduced. When we're looking at ionic reactions that form ionic compounds, we can see, oh, the sodium lost an electron, that's oxidation. When we're dealing with reactions between nonmetals, like carbon and sulfur, and it forms CS2, there's no charges to help us out, and that's why oxidation states were invented. So here, elemental carbon, that has an oxidation state of 0. Here is sulfur, the element, that has an oxidation state. Did I say 2? Yeah. What the heck? That's a 0. Carbon has an oxidation state of 0. I'm not losing my mind. I lost it a long time ago. I've just been faking it. Sulfur has an oxidation state of 0. They form this compound, CS2. So 2 nonmetals, Fe765. Fluorine, hydrogen, oxygen, group 7, no, group 6. Sulfur's in group 6. Sulfur gets to be -2. There's 2 of them, and so the carbon must be +4. So we look at the product here, we assign the oxidation states, and now we can look at the change in oxidation state and identify what's being oxidized, what's being reduced. The carbon went from 0 to +4. If those were charges, that would be losing electrons, right? So that represents its lost electron density. So oxidation is loss of electrons. We can also define oxidation as an increase in oxidation state. The carbon is being oxidized because its oxidation state goes up. The sulfur went from 0 to -2. Its oxidation state was reduced. It was decreased. It went down. That's a reduction. So you can look at the oxidation states. If it goes up, it's oxidation. If it goes down, it's reduction. Reduction means to make something lower. Any questions? Yeah.
An increase in oxidation state. So what if one element has a charge like, let's say, -3, and it goes, in the product it goes to -1? Is that an increase in oxidation state? Would that be oxidized?
Yeah, so if we have something going, nitrogen. So you're saying it was -3, and then over here it ends up being -1?
Yeah.
Yeah, so here the oxidation state would be -3. There the oxidation state would be -1. That's an increase in oxidation state.
Because it doesn't matter that it's still negative, right?
Right. So a -3 is a lower number than a -1. So if you think of, debt, I'm in debt $3 or I'm in debt $1. I'm better off at $1, right? Yeah. Negatives can be weird. Any other questions? We can also look, when we actually have ions, we can look at what's going on. How did the charges change? Well, how do you go from a -3 to a -1? Well, you'd have to gain 2 electrons, right? So reduction is gain of electrons. Wait a minute. My brain just quit. The oxidation state is increasing. That's supposed to be oxidation. Oxidation is loss of electrons. Pause. Okay, my brain has come back. Students, help me out. This is reduction. We were talking about reduction because the oxidation state, we're talking about oxidation. The oxidation state went up. Never mind. Okay, that can be confusing, huh? Right? I get confused myself sometimes, like I just did, very embarrassingly, and I'll put that up on YouTube and everybody can laugh at me. You have to be able to think it through. So reduction is loss of electrons. Oxidation is gain of electrons. Oxidation means the oxidation state is increasing, becoming more positive. If you can think that through, then you can do that even when you do get confused. So let's practice. Here we have a chemical reaction. And it's asking us to identify the element that's oxidized and the element that's reduced in this reaction. Now this is a little more complicated than just sodium and chlorine, right? Because we've got tin, and we've got hydrogen, and we've got nitrogen, and we've got oxygen. We need one thing to be oxidized, one thing to be reduced. Some of them may not change at all. It is also possible to have multiple things oxidized and multiple things reduced. So the way we do this is we identify the oxidation states of all the things involved. Well, tin, SN, what's its oxidation state? 0. Okay. Well, let's just tackle that next one. We've got hydrogen, nitrogen, and oxygen. So we're going to say Fe765. Fluorine, hydrogen. What does hydrogen want? +1. So hydrogen wants +1. Next in the list is oxygen. Oxygen wants -2, so it gets it. And then we've got the nitrogen. So remember here that there are 3 oxygens. Each oxygen is -2. So we have a total of -6 here and +1 from the hydrogen. And so the nitrogen needs to be +5 because overall this is a neutral molecule.
So we're not using the coefficient?
We're not using the coefficient. This 4 is just telling me I have 4 of those. And so I have 4 of the hydrogens, and each hydrogen has a +1. Yeah, so the coefficient is here to balance the equation, but we don't need to look at it at all when we're talking about oxidation states. Excellent question. Okay, so the hydrogen's +1, the oxygen's -2. That makes the nitrogen +5. So let's look at SnO2. What kind of a compound is that? It's ionic. So we have ions here. We have tin ions and we have oxide ions. What's the charge on an oxide ion? -2. So its oxidation state is -2. There's 2 of them. What's the charge on the tin ion in that compound? +4. So its oxidation state is +4. So when we're looking at ionic compounds, the oxidation states are the same as the charges on the monatomic ions like oxygen and sulfur and tin and those sorts of things. We've got NO2. We don't need to look at the 4. We've got nitrogen and oxygen. Who gets first choice? Oxygen. Oxygen wants -2. There's 2 of them. What does the nitrogen have to be? +4. There's 2 oxygens. There's 1 nitrogen. All these oxidation states have to add up to the charge on the molecule, which is 0. This is not hard math. It's just math applied to a very weird and abstract concept. How about water? Fe765. Who gets first choice? Hydrogen. It wants to be +1. There's 2 of them. What is oxygen going to be? -2. In water, hydrogen and oxygen both get what they want. But we give it to hydrogen first because he's first in the list. So any questions about assigning the oxidation states? Now we're tasked with finding what's being oxidized, what's being reduced. And we're looking at individual elements, not a compound. So we're going to look for something whose oxidation state has gone up, and that's the one that's oxidized. So who's gone up in oxidation state? SN. So tin went from 0 to +4. That's an increase in oxidation state. We can also say that the tin has lost electrons because it went from a neutral atom to a +4 ion. It does that by losing 4 electrons. So both definitions give us the same result. So the tin is being oxidized. What is being reduced? The nitrogen. The tin being oxidized is relatively easy to pick out. The nitrogen being reduced, the only way you can do it, figure out which one, is by looking at the oxidation states. So nitrogen went from +5 to +4. Its oxidation state went down. It was reduced. Nitrogen is reduced. So the nitrogen is reduced. The element that's oxidized is the tin. Any questions? So oxidation is loss of electrons. Reduction is gain of electrons. Those processes have to occur simultaneously. If one loses, another must take them, and vice versa. So as if all of that wasn't confusing enough, we have to introduce the concept of these agents. So the reactant that reduces an element in one of the other reactants is called the reducing agent. And the reactant that oxidizes something else is called the oxidizing agent. The reducing agent contains the thing that's oxidized, and the oxidizing agent contains the thing that's reduced. How's that for confusing? Okay, let's think about Hollywood and making movies. So in Hollywood, you have movie stars, and you have their agents, right? What does an agent do? He promotes the movie star and helps them to get parts in the movie, right? Who actually acts in the movie? The agent or the movie star? The movie star. But the agent has a part in it. The agent causes it to happen, although the agent doesn't actually do it. Does that make sense? Right? So the reducing agent here doesn't get reduced. The reducing agent arranges for something else to be reduced. The oxidizing agent doesn't get oxidized. It arranges for his movie star to get oxidized. Okay, let's look at these. Determine whether or not each reaction is a redox reaction. If it is, identify the oxidizing agent and the reducing agent. So to identify a redox reaction, there's a couple of things you can look at. If you have a nonmetal and a metal, the elements reacting, it's going to be an oxidation-reduction reaction, a redox reaction. If you have something reacting with oxygen, it's going to be redox. So those are tip-offs. So if we look at this first one, we've got lithium and chlorine. We have a metal and a nonmetal reacting. So we can say, yeah, that's going to be a redox reaction. But what's being oxidized, what's being reduced? Which are the agents? Well, then we have to look either at the charges or at the oxidation states. And since they end up being the same, it doesn't really matter. So lithium here has a charge of 0, an oxidation state of 0. Over here in lithium chloride, what is the oxidation state or the charge on lithium ion? It's +1. We know that from its position in the periodic table. It forms a +1 ion. It does that by losing an electron, right? Oxidation is loss of electrons, so lithium is being oxidized. Chlorine here, as an element, is a 0. And over here, this is an ion, right? What is the oxidation state of chlorine here? -1. So lithium went from 0 to +1. Its oxidation state increased. That was oxidized, right? So lithium is oxidized. So is that an oxidizing agent or a reducing agent? It's a reducing agent. The lithium is causing the chlorine to be reduced. The lithium is oxidized. It's the reducing agent. So the agents are opposite. Lithium is the reducing agent, then chlorine must be the oxidizing agent. Chlorine is being reduced. Chlorine is causing lithium to be oxidized. So Cl2 is the oxidizing agent. I call it OA. Questions? Let's look at number 2. Is this a redox reaction?
No.
Why not?
Yeah, two metals react.
We do have 2 metals, but what about the charges on the metals? So if we're looking at well, it's not reacting with oxygen. It's not a metal, non-metal, so that does suggest it's not a redox. But what's happening with the individual things here? We could look at oxidation states. Aluminum is 0 over here. And what's its oxidation state over here? That's the product. 3 plus 3. So is the aluminum being oxidized or reduced? Yeah, it's being oxidized. Its oxidation state is increasing. That happens because it's actually losing electrons. And the tin here is going from plus 2 to 0. So the tin is being reduced. The aluminum's being oxidized. What's the oxidizing agent? The tin is being reduced. It's causing the aluminum to be oxidized. So the tin 2 plus is the oxidizing agent. Remember, the agent doesn't actually star in the movie. They arrange for somebody else to star. The oxidizing agent isn't oxidized. It arranges for something else to be oxidized. The reducing agent, then, is the aluminum. The aluminum is oxidized. It's the reducing agent. I hate even having to tell you about this. It's just really kind of confusing, isn't it? Okay, how about number 3? So we've seen reactions like that before. That would be considered a precipitation reaction, right? Because here we have 2 aqueous ionic substances, and we're forming one solid and another aqueous. And so this is our precipitate. We learned how to write complete ionic and net ionic equations for that. What you want to do here is you want to look at the charges on the ions, especially on the metal ones. So here, lead nitrate, what's the charge on the lead ion? 2 plus. So this is Pb 2 plus. It's got a plus 2 plus charge. It's got a plus 2 oxidation state. Over here in the product, what's the charge on the lead ion? 2 plus. It's the same. So is the lead being oxidized or reduced? No. Let's check the other metal. Here's lithium. What's its charge? Plus 1. Its oxidation state is plus 1. What about over here? Still plus 1. We have polyatomic ion in here, nitrate. There's nitrate here. There's nitrate there. That's not changing. And here we have chloride ion and chloride ion. So is this a redox reaction? No. There's no transfer of electrons or electron density. This is not redox. All that's happening is the ions are changing partners, but the ions themselves are staying the same. So that one's not a redox. How about this last one? Is that redox? Something reacting with oxygen. So that's a redox reaction. To identify what's being oxidized and reduced, we have to look at the oxidation states. So here we've got 2 elements as our reactants, so those are going to be 0. Carbon dioxide Who gets first choice? Oxygen. So the oxygen gets to be -2. There's 2 of them. They're each -2. What's the carbon? +4. So who's being oxidized? The carbon. The carbon is being oxidized. So carbon is the reducing agent. Because it's causing the oxygen to be reduced. And so O2 is the oxidizing agent. The oxygen is being reduced. Any questions? Is that a question? Okay. Stretching. So let's look at the combustion reactions. We just learned that combustion reactions are redox reactions. What we identify as a combustion is something reacting with oxygen. It's going to form one or more oxygen-containing compounds. Often these are going to include water. Combustion, if you think about something burning, what happens when stuff burns? Does it get hot or cold? It's hot, right? Combustion releases energy. So here we have natural gas, which is mostly methane, reacting with oxygen, forms carbon dioxide and water. If we look at the oxidation states, in methane, carbon's the -4, and hydrogen is +1. Oxygen was 0. And then over here, now the carbon's +4, the oxygen's -2. The hydrogen has stayed the same, and then there's more oxygen that's -2. So the carbon was oxidized, the oxygen was reduced. In writing combustion reactions, you'll only have to predict products for things where we have carbon, hydrogen, and possibly oxygen in the compound, and that reacting with oxygen. I'm having issues here with my iPad. The products of a hydrocarbon reacting or combusting are going to be carbon dioxide and water. Okay, so how do we do this? So we're told liquid C2H5OH. So that's a reactant. Whoops. C2H5OH. They told us it's a liquid. It's actually ethanol. Combustion reaction. What's the other reactant? Oxygen. So that's going to react with oxygen, O2, because it's a diatomic element. What's the normal state of oxygen? It's a gas. You know, on this periodic table on the wall, the colors tell you what the state is at room temperature. The red ones are gases, the blue ones are liquids, the black ones are solids. Okay, so those are going to combust, and the products are CO2 and water, because you remember that it's CO2 and water. So the products are carbon dioxide and water. So what state symbols should we put on these guys? Gases. So carbon dioxide's a gas. Water, normally we would put liquid, but if we're burning something, it's going to be hot, right? So the water's going to be a gas. I'm not going to try to trick you on that one, but there it is. Now we have to balance it. So here I've got 2 carbons, and over here I have 1 carbon. So I'll put a 2 in front of the CO2. Over here on the left side I've got 5 plus 1, 6 hydrogens. And over here in my water molecule I've got 2 hydrogens. So I must need 3 water molecules, right? To get 6 hydrogens. And then there's oxygen literally everywhere. Everything has oxygen in it here. So in this molecule, I have 1 oxygen. Here I've got 2 oxygens. In my 2 CO2, I've got a total of 4 oxygens. And in my 3 waters, I've got 3 oxygens. So I've got a total of 7 on the right side and 3 on the left side. I don't want to change the coefficient on the ethanol, because if I change this to change the oxygens, it's going to change everything else. So at this point, all I want to do is change the coefficient on the oxygen. 3. So if I make this a 3, then I have 6 there, right? Plus 1 is 7. Sometimes you may end up with needing an odd number of electrons, an odd number of hydrogens, and all you've got over here is O2, and then you get the odd even problem. But this time it didn't happen. Any questions?